divided or classified into three categories. One is metal, and second is semiconductor, and third one is insulator. What is metal by? What is mean by metal? Metal means
The
what?
distance between the band will be less and they are strong.
Yeah, band. There is no band gap. Okay, there is no band gap, and the conductivity is very high.
They are
Okay,
strong.
strong means in the sense what? Strong means,
Conductivity is high.
yeah, yeah. So if you say in conductivity, this conductivity is very high. Okay, we cannot say strong. When we use the strong material, suppose the in strength, suppose if you take plastic or iron, that in that case we will say strong is iron is strong, like that we will use that word. Okay, no problem. So these metals are the high conductivity material because these metals always have very high number of free electrons. These are having very free electrons. Lots of free electrons are available in metals. Lots of free electrons are available in metals. So that if free electrons are available means conductivity also very high. Conductivity also very high for metal. So suppose, and if you come to the insulators, there is no free electrons. No, you can write no free electrons. So no free electrons means conductivity also very less. Conductivity also very less. And the semiconductors are, if you divide this one, semiconductors, semi and conductors. Metals we are calling a conductor because these metals carrying free electrons. They are carrying free electrons. That's why we are calling metals conductor. You can say conductors also. Conductor. These are metals are conductors. Okay, semiconductors means they, the conductivity of these materials, it is lies between the metals and insulators. It is conductivity is greater than the insulator and less than the metals. Okay, it, the conductivity of semiconductor materials is lies between the metals and insulator. It is greater than the semi insulators and less than the metals. Okay, and also here depending on doping and temperature, depending on temperature and doping, the free electrons are available in semiconductors. Depending on temperature and doping, these free electrons are available. Okay, so and here the band gap also like 0. About 6 to about 3 electron volts, about 3 electron volts, but insulator greater than 3 electron volts. There is no band gap for metals. No band gap for metals. What is the band gap for metals? There is no band gap because there is no bands in metals. Okay, so you got it right. Metals means these are conductors. They are having huge number of free electrons. So if large number of free electrons available means the conductivity also high. Okay, conductivity also high. So insulators, there are no free electrons, and there is no free electron means the conductivity also very less, and the band gap is higher. Band gap is very high compared, greater than, above the 3 electron volts. Okay, metals, for metals there is no band gap. And semiconductors means the, this conductivity lies between the metals and insulators. The band gap range is 0.6 to about 3 electron volts. Okay, depending on temperature and doping and impurities, the conductivity of the semiconductor will change. Conductivity of the semiconductor will depends on other parameters like temperature and doping and impurities, like that. Okay, so we'll see that one. Okay, now what is the band theory actually? Depending on band theory, they are divided into three categories. Okay, see here what the band theory, just I will go through just basics only because we don't have in syllabus this topic. So band theory of solids means, band theory of solids, if you say this one, how the energy levels are distributed in the energy, or you can say energy levels of atom. Okay, energy levels of atom. It explains the about how the electrons are occupied in a different energy levels. How the electrons are occupied in a different energy levels. Suppose yesterday we have solved this one, potential particle in a one dimensional box. Here also what they have done, they have a periodic potential. Okay, they have taken periodic potential like this. Okay, they have periodic potential. Okay, this is V, and here zero potential, here potential V, again here is V, and here 0, again here V, again here 0. Like that, there is a, they have taken periodic potential. Okay, periodic potential, and solved the Schrodinger wave equation. Okay, what they have done, Schrodinger wave equation. Schrodinger wave equation. After solving Schrodinger wave equation, so they derived the energy levels. Okay, expression for energy levels, they derived the expression. Okay, using this periodic potential, they have solved the Schrodinger equation, and after that they determine the energy levels of a atom. Energy levels of a atom. Okay, now yesterday we have discussed, okay, energy levels. En is equals n square pi square h cross square by 2m L square, right? Yesterday we have derived the expression for energy level of nth atom. Okay, now what are the allowed energy levels here? What are the allowed energy levels? Allowed energy levels. Suppose I am taking yesterday problem as example. So what are the allowed energy levels here? Japandi. What are the allowed energy levels and what are the forbidden energy levels? Suppose if you, but just tell me what are the allowed energy levels. No, what are the n value? Otherwise, if you, you can take, what are the n values? Possible n
One,
values?
two, three, four.
Yes, one,
One, two,
two,
three.
three, 4, like that, right? So these are allowed energy levels. If you substitute n is equal to 1, 2, 3, 4, n is here principal quantum number, and it is a integer. Okay, it is a integer. So if you take n is equal to 1, pi square h cross square by 2m L square, and if you substitute n is equal to 2, n is equal to, suppose E2 is equals 4 pi square h square by 2m L square. 2m L square. Okay, so if you substitute n is equal to 3, n is equal to, please mute
9
some,
pi.
9 pi square h cross square by
9 pi
2m L square. So these
square,
energies
4 ml
are, yeah, very good. Okay, thank you. Okay, these are allowed energy levels. So here we are not taking 0.5 or 0.6. We are not taking decimal values. These are not allowed. These are allowed. Okay. Suppose if you draw the diagram here, if you draw the diagram. So yesterday also we have drawn this diagram. Okay. So this is E1, that is ground state energy. This is E2, and this is first exerted energy, this E3. Okay, this we have drawn here like that. Okay, here one energy level is there, here one energy level. In this between, this is the forbidden gap. You can say forbidden gap. Forbidden gap. Okay, just I am taking example of this one. So this is allowed energy level, first allowed energy level, this second allowed energy level, third allowed energy level. Okay, depending on these the band theory of solids, what they have done in this theory, what this theory explain means, they have taken periodic potential and solved the Schrodinger equation, and found that or determined the allowed energy levels. What type of energy levels will be allowed for a atom? Suppose if you take yesterday problem, okay, here these are the allowed energy levels. If you take n is equal to 0.5, 0.6, these are not allowed. Okay, so here these are the allowed energy levels. Suppose E1, E2 are there, these two energy levels. Okay, suppose if you take one atom, this one. Okay, for every atom there is how many states available? Suppose if you take how many number of atoms available generally, any material for meter cube, how many atoms available generally? About 10 power 28 or 29, right? About 10 power 28, 29 atoms per meter cube available. Okay, if you take any material, okay, that order of atoms are 10 power 28 to 29 atoms available for a unit volume. Okay, here also there are many atoms. If you take any material, this much atoms are there. If you take one atom, there is a many available states are there, many states are available. So here also there is, we are drawing only one line. Here we are drawing only like this one line, allowed energy levels. But here also there are very fine very finely separated states are there like this. Okay, here also very closely separated states are available. Okay, these we are calling one band. Okay, one band. Here also these states we are calling another band. Okay, the gap between these two are we are calling band gap or band gap or forbidden gap, or what you can say forbidden gap. Forbidden gap, that is in semiconductors zero point 0.6 to about 0.6 to 3 electron volts, but there is no these gaps in forbidden gap in metals. That's why there is no band gap. If you take insulators, this band gap will be very high. Okay, this is the valence, this is the one band and this is the another band. Okay, like this, these are separated very large distance for insulators. In case of insulators, the band gap is very high. Band gap is very high. So for semiconductors, it is a some range. It will be in some range. Okay. So in semiconductors, we are calling this is valence band. This is valence band, and this is conduction band. Okay. This is conduction band. Okay. Now we will see what is valence band and what is conduction band. Okay. Now this is like this way we have describing different bands. Okay, different bands. Okay, now we'll go to the valence band and what is the valence band and what is the conduction band. Okay, so generally these semiconductors also insulator, where generally these semiconductors are insulators at semiconductors are insulators at where, what temperature, did you remember this? Semiconductors are
High
general
temperature.
high temperature, low
low,
temperature, low temperature,
low,
low temperature. Any value? Any value? Any idea? No? No idea? Okay, no problem. Okay, at 0 Kelvin, these semiconductors are insulators. These semiconductors are insulator. 0 Kelvin in degree centigrade, what is the value? 0 Kelvin.
minus 273 degree,
Minus
227.
273.
minus
Uh,
273.
yeah, very good, very good. Minus
Minus
270.
273.
So in a winter we will see just like a 4 degree centigrade, 4 or 10 degree centigrade, that in that also we will feel very cold. So this minus 273 means very low temperature, right? So in this low temperature these semiconductors are insulator. That means why they are insulators? So we will see that one, why these are insulators at 0 Kelvin. First, if you take see before going to this one, so what are the semiconductor materials? First one, we will go to that one. What are the semiconductor? What do you know about semiconductor materials? Means what? Silicon and germanium. Germanium. These are general formal semiconductor. These are general semiconductor, and other semiconductors also there. This is general semiconductor or general primary semiconductors, or you can say compound compound semiconductors also there. These are, if you take a combination of third and fifth group elements and two and fourth group elements, two, two 2 and 4th group elements and 2 and 6th group elements. These also we can say, we are saying compound semiconductor. These also some semiconductors, but different kind of semiconductors. Generally 4th group elements silicon, germanium, and these are the semiconductor materials, and other elements also carbon and silicon, germanium. These are carbon, silicon, germanium. These are general semiconductor 4th group atoms. 4th group atoms, and other semiconductors also there, compound semiconductor, third group elements, and if you combine this third and fifth group element, there is a semiconductor. These also we are calling semi compound semiconductor. Okay, now, so what we are discussing, why these are, this, suppose if you take silicon at 0 Kelvin, these are insulators. So why these are insulator at 0 Kelvin? Anyone? Why semiconductors are insulators at 0 Kelvin? Don't know? Okay, no. So this is the valence band. so this is a valence band. Okay, valence band. I will write side. So this is valence band, or you can write valence band. Here, if you take silicon, if you take, there is a 10 power 29 atoms available. 10 power 29 atoms available per unit value. Okay, unit value. So according to Pauli principle, okay, there is a 10 power 29 electrons will fill or 20 power 10 power 29 states available for a unit value. Okay, per unit volume, or you can say meter cube, whatever. Okay. 10 power 29 states available. In this 29 states, each state we can fill the electrons. We can fill the electrons. Okay. So here also, here 10 power 29 states means each state is closely separated by one to other, one to another. Okay, like this, each closely, very closely separated. This like this. Okay. So these we are calling a valence band. These states we are calling valence band. Here also in the conduction band also states are very closely separated. Very closely separated. Okay. These we are calling conduction band. Okay, I am writing completely now. Conduction band. So generally at 0 Kelvin, we are considering, suppose if you take at 0 Kelvin, if you take any crystal or any semiconductor material at 0 Kelvin, all electrons are occupied in a valence band only, in a valence band only. Okay, valence band only. Okay, suppose. So these electrons are bound to each other. These are, suppose, what is the bonding in a silicon? What is the bonding? Which type of bonding will be there? Silicon and silicon. Don't know. Okay. Suppose this is silicon. Okay. Silicon. What is the electronic atomic number? What is the atomic number? Atomic
14.
number.
14.
Atomic number is 14, right? So if you write configuration, 1s2, 2s2, 2p, 6, 3s2, 3p2, right? 3s2 3p2. So this 3s2 3p2 is the valency electrons are valency configuration, 3s2 3p2. So that means 4 valency electrons available for silicon. For silicon, 4 valency electron, 2 are in s orbital, 2 in p orbital. So that means 4 valency electron it has. Okay, right? Here 4 valency electron are there. So these silicon will share this one electron to neighboring silicon, make a covalent bond. Make a, this silicon always forms the covalent bond. Here also some neighboring silicon. Here also neighboring silicon share the one electron and makes the covalent bond. Here also some neighboring silicon shares one more electron and they make the covalent bond. Okay, covalent bond. Okay, this is bond, not band. Okay, so silicon, by sharing each electron, that will make covalent bond with neighboring silicon atom. Okay, see, at 0 Kelvin, these electrons are tightly bound to the nucleus. Generally, suppose this is the nucleus, electrons revolve around the nucleus, right? At 0 Kelvin, these electron tightly bound to the nucleus. This electron tightly bound to the nucleus. So all electrons are filled in the valence band only. These are all electrons filled in the valence band, but these electrons are not free. These are bound electrons. These are bound electrons. That's why in, if electrons are available in valence band, we will not get the current. That means there is no flow of electrons. So whatever electrons at 0 Kelvin, all bound to the nucleus, and these are not free because all are bound to the nucleus. These are some binding force will be there. So at 0 Kelvin, this is the situation. Now how will get the conductivity, or how will get the current in semiconductors? Suppose, but where we are staying generally at 27 degrees centigrade. 27, around 27 degrees centigrade. Suppose if you increase the temperature, maybe room temperature at about 27 degrees centigrade, so these bound electrons getting some thermal energy. Bound electrons getting some thermal energy by this temperature. Thermal energy means if you heat the material, that electrons getting some thermal energy. Okay, so here see, once we get these electrons get the some energy, whatever electrons in the bound electrons in the valence band, they will get energy and they will jump into the conduction band. They will jump into the conduction band. Here, in this conduction band, these electrons are whatever electrons came from valence band, these are free here. Whatever electrons in the conduction band are free. That's why we are calling this band as a conduction. This band, whatever electrons available in the conduction band, conduction band are useful for current flow or conduction, or you can say conduction or current, or whatever you can say. Okay. So if you increase the temperature here, if you increase the temperature, the bound electrons in the valence band get the thermal energy and they will jump into the conduction band. They will jump into the conduction band. Once they jump into the conduction band, they are free. They can move anyway, any direction they can move, because they are not bound to the nucleus. That's why we will get the current. If you use the semiconductors, we will get the current. Okay, if you use any semiconductor, you will get the current by, but we are living at 20 around room temperature, that is like 27 degrees centigrade. So if you use semiconductors at 0 Kelvin, there is no use. It's like a behaving as an insulator. But if you use at room temperature or a higher temperature, the conductivity will increase. Conductivity will increase because most of the bound electron in the valence band break the bonds, break the covalent bond. Here see. So here also these electrons getting some kinetic energy and they break the bond and they will jump into the valence band. Okay, they will break the covalent band and jump into the conduction band. They will become a free electrons. Okay, once they are free, they can move anyway, any direction. So then we will get the current in a semiconductor. Okay, this is the difference between insulator and semiconductor. In semiconductors also, insulators at 0 Kelvin, that is very low temperature. But if you give some temperature, all bound electrons in the valence band, okay, bound electrons in the valence band, they will break the bond and they will jump into the conduction band. They become a free. Okay, right? Did you understand this one up to now? Did you follow the uh, okay, now
Yes, sir.
this is the general semiconductors. Okay, now these semiconductors are two type. Semiconductors are generally two type. Okay, I am writing shortcut semiconductors. One is intrinsic semiconductors, and second
Extrinsic.
one is, yeah, very good,
Extrinsic.
extrinsic semiconductor. Very good. Okay, extrinsic semiconductor. So intrinsic means what? What is the intrinsic? Intrinsic, do you know? Okay, if you don't
Low,
know also, check. Intrinsic means what?
pure form of semiconductor.
Low conductivity.
Pure form of semiconductor.
Pure, very good. Okay, so intrinsic means it is a pure semiconductors. Pure semiconductor, there is no impurities. No impurities. We are not adding any atoms to the this pure semiconductor. Suppose if you have any material, if you have any semiconductor material, it's as it is pure. We are not adding any impurities. Extrinsic means it is impure.
Impure.
Doping
Impure,
is applied.
yeah, doping
Impure.
some. Yes, very good. Impurities are adding. Impurities are some other atoms, other elements or other atoms, you can say. Other atoms also. So why we are adding impurities or doping? So adding adding impurities or you can say impurities are atoms, we are calling doping. Doping means what? If you have a pure
Adding
semiconductor,
impurities.
we are adding some
Addition of
elements or
impurities.
impurities are some other atom, neighboring atoms or some different atom. Then this process we are calling doping. So why you need to add these impurities? Question is here, why you need to add impurities? Why you need what is the drawback of intrinsic semiconductor?
It is less conductivity.
Yeah, very good. Less conductivity, because see here in intrinsic semiconductor, whatever we have discussed here. So how we are getting conductivity in intrinsic semiconductor? By thermal energy only. If you increase the temperature, whatever available electrons in the valence band will jumping into the conduction band and they are becoming a free. Then we are getting the current, right? This in intrinsic semiconductor, we are getting current only due to temperature, only due to temperature. So in that case, we are getting only less current, less conductivity. The intrinsic semiconductors conductivity is very low. To increase conductivity, we are adding extra elements. Then we are increasing the conductivity. We are increasing the conductivity. That's why we are doping a semiconductor. We are doping a semiconductor. Now there are two type of in if you extend a semiconductor, we have two type. One is p type semiconductors, another is n type semiconductor,
N
right?
type.
So p type means majority are holes here, majority are holes. N type means majority are electrons.
Electron.
Now okay, good. Now we will see how this p type is forming, how this n type is forming. Okay, right? So generally this n type is formed if you have a fourth group element, that is silicon or germanium or like that. If you add fifth group elements, that is phosphorus or antimony or bismuth, okay, some etc like this. Okay, if you add this fifth group element, you will get the n type semiconductor. Now we will see here in p type, if you add third group element atoms to fourth group elements, that is boron, aluminum, gallium, okay, boron, aluminum, gallium, etc, okay, to silicon, germanium or like that. So here you will get the p type third group. If you combine third group, fourth group, you will get p type, and if you combine and fourth group and fifth group, you will get the n type. Now we will see how this n type p type will form. Okay, right? So first we will take n type. So first you take a phosphorus fifth group means what? So fourth group element means what we said. What is the valency of fourth group element?
4.
4 electrons, right? Here fifth group means what? 5, right? Valence is 5.
5.
Here also 5 electrons are available. So here phosphorus having 5 electrons, right? Here they have 5 electrons. Okay. So here 4 electrons are already there. So these 4 electrons is sharing with neighboring silicon atom, okay, making a covalent bond. Okay, one electron sharing with neighboring silicon atom and making covalent bond. But this phosphorus having one more extra electron, one more extra electron. This is ready to give, ready to donate, or ready to give. This phosphorus having one extra electron to make another covalent bond. So this silicon, if you draw the network, silicon network, it like this. Okay, here also some silicon, here also some silicon, like this you can have a network, silicon network. Here also some silicon, here also some silicon. Okay, so what this one will do, this will break the this electron, and or you can say this electron, what they will do, they will come here and they will make the covalent band. They will eject this electron, they will eject this electron. So that here free electrons are available. This electron making bond with making collision or making replacing this electron, or you can say this electron replacing another electron in a covalent bond. And one again, here we are getting a free electrons. Here one extra electron is there already, one electron made covalent bond, but still one extra electron is there. That's why in this way, if you adding more phosphorus atoms, more electron will increase, more electrons will increase. If you increase the more fifth group elements, more number of fifth group elements to silicon, more number of electrons will increase in this process. Okay, in this process. That's why here majority carriers are electrons, here majority carriers are electrons. So this phosphorus is donating one electron. That's why this phosphorus atom, what we are calling donors, what we are calling donors. So this phosphorus is donor. Okay, now you got it right, how the n type material is forming. If we add fifth group elements to fourth group elements, we are getting extra number of electrons without creating electrons. That is n type semiconductor. Now see what is
Sir,
whole here.
once again,
Once again, okay, see here fifth group phosphorus having how many electrons? Phosphorus having 5 electrons, right? 5 electrons, each phosphorus sharing 1 electron to neighboring silicon atom. So if it is a material, means there is no only one atom, there is several atoms. So suppose silicon is like this, structure is there, okay, silicon like this, like this, okay, like this, okay. Silicon network is, this is, we can say, silicon network. In this network we are adding one phosphorus, we are adding one fifth group element. This phosphorus having 5 electrons, 5 electrons. So 4 electrons will make 4 electrons will make 4 covalent bonds with a silicon atom, right? But phosphorus having one more extra electron, so that is ready to donate or ready to make another covalent bond, another covalent bond. So in that way, like that, if you increase the phosphorus atoms, more number of free electrons are available, or these free electron replace another electron in a covalent bond, like this, okay. This electron, what this will do, this electron, suppose phosphorus having some binding energy is different, silicon binding energy is different, right? Binding energy is different. So these are, compared to silicon, the binding energy of phosphorus is less. So these electrons are getting some thermal energy, or you can say these are easily free by same, if you give same temperature, suppose we are giving 27 degrees centigrade here, these phosphorus binding energy low, so these electrons are easily break the bond, okay. Once this break the bond, they will replace another electron in a covalent bond, like that this electron will replace another electron, like this. In a system we are, more number of electrons are increasing if we increase the phosphorus atom, if you increase the phosphorus atoms, okay. So just again, okay, just a minute, I will explain one more time. Yes, so this is phosphorus atom, or you can say silicon network is there, like this, okay. We are adding one phosphorus atom to silicon, phosphorus atom. So here phosphorus having 5 electrons, silicon having 4 electrons. So if you draw on diagram, so this one sharing 5 electrons, like this, it has a 5 electron. So each electron, phosphorus sharing 1 electron to silicon and making covalent bond, okay, making covalent bond. Here also making covalent bond, silicon, okay. Here also making neighboring silicon, and silicon also share 1 electron and make covalent bond, okay. Like this, silicon is making covalent bond, but this one extra electron is there. So phosphorus having one extra electron, what this will do, here also some covalent bonds will be there, okay. Not only one bond, there is a several many bonds are there. This binding energy is less, so this electron, what this will do, this is free. Once they give some temperature here, once we give some temperature, this electron will be free, okay. After that, this will replace this electron, okay. This electron also getting some thermal energy, and this electron will replace some another electron, okay, some other electron. So like this one, if you add one phosphorus atom, you will get one free electron, one free electron. So if you increase phosphorus atoms, you will get, electron concentration also increase in n-type semiconductor, like this. If you add fifth group elements to fourth group elements, we are increasing the number of free electrons. That's why we are calling n-type semiconductor, this one n-type semiconductor. So once this
Sir,
phosphorus, yes, yes, Amma, please
free
ask.
electron replaces only electron from neighboring atoms, sir.
Yes, yes. That bond is breaking. Okay. This free electron, whatever phosphorus having free electron, right? This is once they get the thermal energy. This once we are giving. Suppose if you give room temperature also, whatever electron in phosphorus getting some thermal energy. Okay. This will break the neighboring covalent bond. Okay. Like that, here also once this electron break the bond, this electron break the bond. This electron will